S to the I to the M to the P. If you want.
Thinks
Recording
they'll
in
need an
progress.
extension for this next set, 7, 1, 4, 2, and 3, just shoot me an email preferably by like Saturday or Sunday, because then I can do this for you, right? But if I do not hear by, a reasonable time, I won't be able to do it. So I'll just repeat one more time. If you think you're going to need like homework extension or anything like that, just send me an email. I did extend the homework that was due on Sunday, like from last week, to be today. But again, I'm pretty sure everything is just for Sunday. So the homework this week, it will be due Sunday evening at midnight. If anyone needs an extension, I will extend, and I'll probably do 6 o'clock this time. I meant to do 6 last time. So I would do 6 o'clock on Tuesday, because then we start new material. So I would want the homework to be done before class. Granted, unless somebody sends me an email that something crazy happened, or they're in the hospital, or they, whatever trouble you have, this is fine. Just send me a note. Okay. So today we're doing these applications of right triangles, and a little harmonic motion. So we are back to some of these right triangle fun, or not fun for some people, but I promise you're going to be okay. The second time you see something, you always get it better. Even if you don't think so, I'm telling you, that's true. So we want to solve this triangle and round the lengths of the sides to 1 decimal place. So we'll be using the Pythagorean theorem or the fact that the sum of the 3 angles should be 180, right? So let's see. So they give us side A, they give us side C, and they tell us it's 90 degrees, right? Cool. And they don't give us side B. So we can just use, and notice one thing you want to notice too, just in the way they're doing this, they're setting this up for something not related to right triangles. So those of you will be happy about that. But notice how A is across from A, B is across from B, and C is across from, and C is across from C, like little c and big C, right? This is on purpose, and this is going to be done for the rest of these triangles. And then when they're not right triangles, we have some special things we're going to do. So first we can do Pythagorean theorem, right, to get B, little b. And when it says solve the right triangle, the A, B, and C, those are the actual angle. So we know that big capital C is 90 degrees. Capital B and capital A, we have no idea. So we'll have to find that using our trig later. But first we'll do the Pythagorean theorem since we have a right triangle. So I'm going to say we need to make sure C is the hypotenuse. So this is right. So we'll do 9 squared plus B squared is going to equal 20 squared, right? So B squared is 400 minus 81, because 9 squared is 81 and 20 squared is 400. And what I'm doing there is subtracting 9 squared from both sides so that it cancels over here, right? Oops, okay, now I've lost this color. It's something like that. And then that means B squared is 319. Okay, possibly a gross number. So we're going to get decimals here. This is okay. We're just going to do that. That's totally fine. So I take the square root of both sides and I get B is approximately, let's say exactly 319, square root of 319, which then will approximate, just because in this case, I'm not so worried. So lucky for you, I'm not so worried about the square root and simplifying, but it's about 17.9. We'll just round to 1 decimal. Oh, it actually said round the sides to 1 decimal place. So I should read directions, right? So, okay, so we get B is about 17.9. Okay, so that's that check. All the sides are good. We got one side, two side, 17.9, third side. Now we need the angles. So I do know this is 90 degrees, right? C. So I know that I could find angle A by doing anything I want really. But if I just do sine, that's opposite over hypotenuse and it doesn't involve decimals. So maybe I'll do that. So I'll say sine of A is 9/20, right? Which this means that A equals, and we know this now, inverse sine of 9/20, right? And put this in your calculator and let's stick to degrees, because that's, well, at least, okay, this is what I solved for here. If you did radians, that's fine. I think we're going to mostly use degrees. But if I put this in my calculator, it should be about 26.7 degrees. So this is my A. And we know that, so this is A. So now we have A is here, C is here. We're left with B. We need to figure out what is this angle. Now, instead of doing, there's the dogs. Instead of doing right triangle trig, right? Oh. All right, we're just gonna power through this. Okay. Instead of doing right triangle trig here, oh, this is bad. All right, let me put them away. Hold on. Okay. They might still bark, but they'll be gone in just a moment. Just take them outside because they're barking. Okay. So we're gonna instead use this right here, so we don't have to do any more trig. Yes, you could do trig again. I mean, if you love it, for those of you that love it, go for it. And you might just get like slightly off, like if you round again. Oh, audio is not, is my connection funky? Okay, so sorry, I'm seeing a bunch in the chat. We use inverse because it's asking for angle. So first, Veronica, yes, we use inverse. No, sorry. Yes, we use inverse because it's asking for angles. So, yes, inverse, since we want angles, right? And if you didn't hear the dogs, that's because my computer blocks it out pretty well. But I hear them, and so it's just hard for me to talk to you. And then Michelle and Veronica, if it's not good, I can switch to audio on my iPad if that's better. So message again, and okay, it sounds good now. And Michelle, I will say, like, your video was a little slow. I don't know if that's on my end or your end, right? So if it's really, really bad, message in the chat again, and I can try to switch to the iPad audio. Yeah, so, okay, I'm sorry, Michelle. And if you want to try turning your video off, I don't know if that helps. Again, it may not, up to you. Okay, and if you can do the encrypt, or the, what the heck is that called? The voice, I don't know how you do it. Where's Jakob? If he's here, he knows how to do it. But enabling my, oh my gosh, I don't know what it's called.
Closed captioning.
Yes, thank you, Michael. I knew somebody knew. If you want to enable closed captioning, Michelle, that might help, because I know it helped Jakob. So yeah. Okay, so back to it. So to get B, we're just going to say A plus B plus C has to equal 180, and that's 26.7 plus B plus 90 has to equal 180. And so, okay, I'm just gonna do some mental math here, except maybe I shouldn't, but I'll write what I did for you here. So I would subtract 90, subtract 26, right, minus 26.7, because then I don't have to do math, right? And we can just do this. And we get our answer, which should be like 3.3 degrees, right? So now we have B, we have A, and we have C. And we got also this little b down here. So we're just solving for all the parts of the triangle. Now, there is a way to do this. We're going to look at this application question first, but then we are going to learn, oh, and then we do a little bit of something with graphs. Okay, so maybe this is actually next class that we do those fun formulas that I was thinking of. Yeah, it might be next class, but there is a way. It's called, if you've heard of it before, cool. If not, no worries. It is called law of sines and law of cosines. And it's when you don't have a 90-degree, a right triangle, there is actually still a formula with sine and cosine involved where you can calculate the side or the angle, you know, depending on what you're looking for using this law, right? So just a little fun fact that we will get to it. I'm assuming it's Thursday, but first we're going to stick to all the right triangle goods. So this application, let's see what this says. To determine the height of a window in the top of a lighthouse. So we have this lovely drawn lighthouse. 2 measurements are taken from the ground, 90 feet from the base of the house. So what they're telling us is this is 90 feet, right? From here to here, 90 feet, right? And they're saying 2 measurements are taken. The angle of elevation from the ground to the bottom of the window is 36 degrees. So elevation angle is the one looking up. So they take it from the bottom of the window, from the top of the window. So for the dotted black line, they said it's 36 degrees, the angle of elevation. And then for the angle of elevation from the ground to the top of the window, right, which is here, the red line is 42 degrees. Okay. So that was all the important things in our problem. Angle of elevation. We want to know the height of the window. We don't know that. And we know it's 90 feet, bless you, from the base. Okay. Oh, sorry, that wasn't on Zoom. Okay. So now we have these measurements, right? And we would have 2 triangles. So one of them would go here, right? And the other, if I get back to this, would be, you know, here with this dotted line. Ooh, they're very similar, right? And the other one would be with the red dotted line. So it would be like black line here, red line there in the bottom, right? Now these are both, like, these are 90 degrees. This is still 90 degrees, right? Okay, now what we're gonna do, it says find the height of the window to the nearest foot. So not even the height of the lighthouse, we want the height of the window. So what we're gonna do is we're gonna label this, this little piece as X and this bigger piece as Y. So the height of the window will be our X, and then the height up to the window will be our Y. Now I don't know why it should really ask for both. Or wait, to determine the height of a window at the top of the lighthouse, 2 measurements are taken. Yeah, or maybe X is really the whole thing. No, we're doing it this way. So this entire thing is X plus Y. Okay, so let's do this, right? So first, so we can't just find X by itself. And why can't we? I actually don't know why, if that would work, but we're gonna find X or Y first. And then, we can't find X by itself because if I use the red triangle, I'd find X plus Y, right? So then we have to find Y to subtract it to get X, right? Okay, here's, my brain was mush, but now we're better. So if you weren't following me there, in order to find little X here, what we do is we use the red highlighted triangle and we find X plus Y first. Then we subtract, we'll use the blue highlighted triangle and we get Y and we subtract that. And then there's our X, right? Okay, so let's do this. So first and maybe I'll start with, doesn't matter if it's X plus Y or Y, but if I start with the X plus Y, that's the 42 degree. So I'll have tangent and what I'm looking at is this is the adjacent side and this is the opposite for all of these. So I'm using, in SOHCAHTOA, I'm using opposite and adjacent. I'm never using the hypotenuse. I don't know what this distance is, nor do I care. It's not going to help me, right? So tangent of 42 degrees is going to equal X plus Y divided by 90. You could call it W or something, but then you're going to eventually have to realize, oh, I have to subtract y from this to get x, right? So this means that I can multiply both sides by 90. And then I would get x plus y equals 90 tangent 42 degrees. And this is about, oh shoot, I didn't get it. So 90 tangent, someone can type it if they get it, but I'm gonna have to Google it. It's about, not 200, what is this?
$81.
Yeah, is it 81? I was getting, I don't know why I was getting 100, but that's not right because it was doing it in radians. There we go. 81 point, oh, okay, 0.04 or just 81.0, but I'll take it to it, and it says round to the nearest foot. So in the end, we're going to be rounding this anyway. But does 81 about, right? And then what I want to do is, this is x plus y. So to get, right, this is x plus y right here. So to get just x, now I need to find y. So I'm going to say tangent of 36, which is the other angle right here, is opposite, which is y over 90. I can multiply both sides by 90 again. And I get y equals 90 tangent 36 degrees. And I'm getting, I don't like how I wrote that, 36 degrees. And I'm getting about 65.4. Oh, not degrees, just 65.4 for y. And this was in, I think it was in feet or something. Yeah, it's in feet. So now the cool thing is I can take, so follow me here, right? Y is this guy. So I can plug this in here or just say minus 65.4. And this is going to get me, it will solve for me x. So I'm going to say x equals 81, and maybe I'll get rid of this 0.04. It's not going to really do anything. But minus 65.4, and this should get us about 15.6. And so the window, so what this tells us, so x is this, that's great. So what was the question? The height of the window to the nearest foot. So the height of the window is about, and I'll round that up to 16, so 16 feet. It's pretty big. Well, maybe it's not a big window, but I guess for a lighthouse, it's probably not big, but for like a house, could you imagine if my ceilings probably aren't even 16 feet. Cool. All right. So the lighthouse, the window is 16 feet. Very nice. Now we have this concept of simple harmonic motion. So let's see what this is.
So the other topics that were covered in that section was bearing. Are we not going to talk about bearing?
Yeah. So I'm not positive. I can't answer that with a yes or no for certain, because I know that we are doing like 7-1 and 7-4 mixed. So it's kind of weird that we wouldn't talk about bearing. I feel like we will. I just don't know. Yeah, I don't know. I don't know if they either skipped it or decided, let's mention this later, right? But it could be skipped. I really am not sure. And if it's in your homework, but we skipped it, then let me know, because the coordinator of this course should know that. Yeah, can we skip it? Yeah, I mean, I'd love to skip it too, or just one less thing for me to be worried about. But yeah, I would say, excuse me, I would say if it's in your homework, it looks like we're skipping it just for me, like glancing at the rest of the notes. But if it's in your homework, just let someone shoot me an email. I mean, I probably won't have time to check this week because life, but this weekend I probably could. But if it's in your homework and you notice, definitely just shoot me a message, because I might even go in and just take it out of the homework. But I'm assuming the coordinator who like did all of this, did that on purpose, right? So fingers crossed, let's hope, because I know she adjusted these notes for this semester. So specifically. So yeah, but that is a good question. And I don't know why it skipped, right? I'm not sure. Okay, but they decided to do harmonic motion, which I've actually never done. I've taught bearings, but I've not done harmonic motion. So we're about to find out what that's about. So this is involving the graph of sine, cosine, like this curve, right? And it says, consider a block moving up and down attached to a spring. Like, okay, interesting. The model describes the vertical displacement D as a function of time T after release. So you could either have, what they're saying is, I don't know why you would have a block on the end of a spring, but maybe we'll find out in one of these problems. But what they're saying is, if you have this block on the end of a spring, the motion that it goes up and down at with that weight, they're claiming here that this model, the vertical displacement, which they're D and D, right, is either following A sine omega t or A cosine omega t. Oops. So let's see what that's all about. And here comes something we've done before, right? Amplitude, period. We have not seen frequency, but very similar, but we've seen amplitude and period before. And it looks like it's really similar. The amplitude is going to be the absolute value of A, that first number. So if it's 1, amplitude just 1, right? If it's nothing. Period is still going to be 2 pi, because sine and cosine have a period of 2 pi, divided by omega, which, remember back in the day when we did our transformations, it was like B times T or BX or something, right? And it was 2 pi over B. So nothing has changed here in terms of nothing has changed in terms of amplitude and period. These are not new. But what is new is this frequency measure. And and I even have in my notes, this is like similar to I guess it was section 5.5 graphing. I mean, you can refer to it if you'd like, but and then this is similar to when the period was 2 pi over B. Maybe I should write what I'm saying, right? So now this frequency that we have is the number of cycles per unit time. So now instead of like X, we're looking at this in terms of time. And so instead of like, even though normally it represents an angle, even though it's being plugged into a trig function, so it needs to be, it needs to sort of represent an angle in this sense, but it's representing our time starting at 0 and going on. And notice how, like, for both of these, like, we're never going to graph, like, it's always going to start at 0 and then progress positive. Like, we will never have, anything before that. So, and notice how sine, so, okay, let's make a few notes here. Sine starts at what we'll call equilibrium, which is just 0, right? Because it starts here. And then cosine starts up here. So notice that this starts at an extreme value. Oh my gosh, sorry, an extreme. And the reason for this, so like at t equals 0 here, well, cosine, I think they're just saying, like, picture the block not being fully dropped. Like at t equals 0, it's still held maybe, or it's like up. And again, this is their model. So I am not in control of this, but this is what we are given. And as I said it, but I didn't write it, I want to say that omega, which is like a curly W to me, this is a Greek letter, and that's what that little this little W inside both of these are. And you can think of this as being similar to like A cosine or sine bx minus c, except that there's no minus c because there cannot be any shifting, right? So for this, there's no shifting because we have to start at t equals 0, right? Because we don't start when time is negative or, oh, start 1 second in, like that just doesn't make any sense. And yet so Jakob asks, is each block representing a frequency? Each block is representing a moment in time. I guess you could say, I don't know if that's like, so the frequency is the number of cycles per time. So maybe it is representing maybe one of the cycles, right? In like, I guess we're in hertz cycles per second. But I wouldn't say necessarily it's representing the frequency because like we could calculate the frequency at that time, but it's representing like a moment at t equals whatever this is. Then this block is at t equals here, then t equals. It's just as time goes on, this block that's flying on a spring is following a sine or cosine curve. Again, I mean, kind of strange, right? Now, number one, notice, I mean, if you look at the equation, notice the equation for frequency and how it is maybe similar to another equation that we have. So looking at this first question, it says, how are the frequency and period related? Well, frequency and period, yeah, sorry, we'll try to get through it as quickly as possible. But frequency and period are reciprocals of each other, right? So they are reciprocals, right? Because frequency is omega over 2 pi, whereas period is 2 pi over omega, right? And then, so number 2 is asking if the period is 0.25 seconds, remember period, instead of being in like degrees or anything like this, we're now in time, so seconds. Then the frequency is how many hertz? Well, this is 1 over 4. And so flip it, and the frequency is 4 over 1. So 4 hertz, right? And if we look at, like, possibly we can try this. Let's see. If we look at a graph and say we started, let's see, did I draw enough? 1, 2, 3, maybe it has to go like this. I'm trying to draw this 1 second. And we have something like, we have it broken up. Oh, maybe I drew not enough. But if you have something like this, so this is like 1, 2, 3, 4, 5. This is in fifths. This is like another just example that I think your book gives. 1/5, 2/5, 3/5, 4/5, and 1, right? If it looks something like this one frequency, if you want to know like what is a frequency, I mean, it's similar to well, a period, it's the reciprocal, but here, oh, and I drew this wrong. I think 1/5 is supposed to be, well, okay, maybe ignore kind of, because I was supposed to draw it so that in 1/5 a whole frequency, like you get a whole period. So maybe this isn't helping, and maybe an example will be better. But it's supposed to go like this, and then like repeat this for each fifth, right? Something like that. And this would be where the period is 1/5, except again, I like messed this up. Maybe we'll just stick with the one I drew. So the one I drew, the period is 2/5, right? So one period goes in one whole, like wherever it repeats, one whole snake or like motion, right, of this function. And so we can see here that one period here is 2/5, which means the frequency is 5/2, which is 2.5. Okay, so just to see how to calculate something, and like what it might look like. So, we'd have like in this picture, I drew, well, and I guess what the frequency is representing is the number of cycles per unit of time here is 1 second. So we're specifically looking, unit time is 1 second. That's why they said cycles per second. So if you can see, this is why I wanted to draw this, but I guess this one works as well. You can see I have one period in yellow, 1 period in blue, and then I have a half of a period in green, and then I'm at 1 second. So per every 1 second, the frequency is actually 2.5 periods. That's big, okay, I don't know if that I said that totally right, but that's what it's representing here. So in number 2, if the period, I should have drawn this one, I guess, but if the period was 1/4 or 0.25 seconds, then the frequency, that means at 1 second, it's gone through 4 periods. Okay. Now,
A cycle is kind of like,
yeah.
a cycle is it how long it takes for, say, the block or the object to get back to its starting point?
Yeah, and it should be that. Yeah, because I think we're hoping maybe that happens in 1 second, or something like that. I'm not really sure, right? But that's the idea, I think, well, what you're saying, right? Because 1 period might happen really quickly, whereas we want it to like bounce and then stop, right? Or something. Right? That's what it seems.
Simple harmonic motion is like there's no friction or air
Right.
resistance.
So we're also assuming like the craziest situation that's not realistic, right?
Theoretical, yeah.
It's very theoretical, yes. Which maybe is why Jakob doesn't like this section. It's very theoretical. However, majority of my graduate studies were theory. Although now I'm in the applied world, but I do get it. It's hard. And it's hard to imagine because you also can't, like, I'm trying to explain it to have it make sense, but because, like Michael said, we're ignoring, extra pull or like any wind or any error, we're ignoring like everything and pretending this is our imaginary world where there's no, extra gravity pulling it, or it's just like happening based on the length of the spring and the weight of the block,
It goes forever.
So, yeah. We're just pretending we're in this world.
Right. It's kind of weird.
So now what it's saying here, suppose that an object moves in this simple harmonic motion. So this is what Michael just described, right? With a displacement d based on the formula they give, right? So they give us this, we don't come up with that. And now we're in inches and still in seconds per time. So, well, I don't know if we ever were in anything else, but the distance can be, feet, centimeters, inches, whatever, right? But in this case, we're in inches, and we want to find the amplitude, period, and frequency. Okay, so this isn't so bad because although the concept is pretty outrageous, right, or theoretical, all we need to know are these 3 formulas that we discussed right here. So this is the nitty gritty of it, right? Which we can handle that. We know how to do that. So A is just the absolute value of this first number. So A here is just 30. And I'll even do number 4 at the same time. It's 40, right? Then, and so I'll take this, right? Then we want P is 2 pi over omega. I'm going to highlight omega here and here, right? So P is 2 pi over omega, which in this case is 4 pi. And then let's just simplify that. Pi over pi cancels, right? And 2 over 4 is 1/2. Okay, so my period is 1/2. Now, they showed us the graph here to the right, or maybe we have to match it. I'm not really sure. I'll take a look. I'm not entirely sure because these graphs are actually different than the graphs that are in mine. So I'm wondering what the heck is going on here. But for number 4, I see pi over 8. So I have 2 pi over 8. Okay, if you're not a fan of this fraction and a fraction, remember it's just 2 pi over 1 times, so 2 pi times the reciprocal, so 8 over pi. So again, my pi's still cancel, which is nice. They won't always, but they do in this case. And it's 16, 8 times 2, right? So this means, and when we're talking about period, that we're in time still. So this is 1/2 of a second and 16 seconds, right? Which means my frequency is just the reciprocal. Take your final answer, flip it. Like, how exciting, right? So my answer here for frequency is going to be 2/1, which is just 2. And it says hertz is the label here. So we're 2 hertz, right? And what this means is that per 1 second, we go through 2 cycles, right? And then F here is, instead of, this is like 16/1, right? If I flip it, it's 1/10 hertz. And that means that there's 1/16. This is cycles per second. So we don't even get an entire cycle in 1 second. And this is because the period is 16 seconds. So this one, it happens for a while, right? Now, I want to say that these graphs coincide with what we just saw, but I'm kind of wondering that they don't, because they're going, like, we never graph negative in this case. So I'm thinking these graphs are something different. And it looks, you know what? They're good. For whatever reason, they just go before. I don't know. We always want to just start at 0 in this case. We always want to start at 0. And this was sine and this was cosine. They should be at different. Yeah, I'm not entirely sure what's going on here, but you can see that if you follow these, this one period is at 0.5. And then by the time we get to 1, if you follow it again, 1 second. So like, this is 1/2 a second. This is 1 second. And we can see that we got 2 cycles, 2 hertzes, I guess. Right. And then for D, for number 4, looking at this, it's 16 seconds. So this is coinciding, like 1 full period is 16 seconds, right? Because it stops there. But then at 1 second, which is like here, if we, took all the time and broke this up into 16, that would mean that this is 1/16. So I could like separate this. And what you would do to do that is at each 2, 3, 4, like you'd separate, okay, here, then here, then here. And you'd keep doing this for every, and you'd see 8 or 16 pieces inside that one cycle. So what we looked at is 1/16 of a cycle at t = 1 for this problem. And good news is you don't need to graph these. These graphs are either going to be given, well, for now, I guess we might be looking at one graph later, but I don't know. I think you're be tested. Like, I don't think you're ever going to have to graph these on a test or anything. So, and I know you won't on a quiz, so don't stress about that. But you'll be given these graphs more so for a visual, and really what we are most concerned about is this whole amplitude, period, frequency. Can you calculate it, right? So like, for example, looking at number 5, applications of right triangles and harmonic motion. So again, we're given our D, we're even given the graph, right? And maybe the graph we can just verify, but don't stress so much about the graph because you do not have to do this from the start. But we can see my amplitude, it's like there's a 1 in front of here. So my amplitude is just 1. My period, now this one does have a shift. So this must not be representing maybe harmonic motion. Maybe this is just, I don't know, some type of graph, because it does have a phase shift. So now we're just, I don't know if this is a review or what's going on. But we'll take a look because the next part doesn't have phase shifts. I think this is just a review problem to throw it back and try to see if you remember what this is like. So period in this case would be, here's my omega, right? So it would be 2 pi divided by, oh my God, I wrote omega, but divided by pi, which would just be 2, right? And this is again, I mean, you don't need to write the label, but it's seconds, just so we know. And if you want to remember, like period is seconds per cycle, but frequency is cycle, per second. So what this tells us is that in 2 seconds, 1 cycle happens. So, I mean, if we look at this graph, we'd follow it to 2, all the way to 2 seconds. That's 1 cycle. And this looks more like cosine, or maybe this is the sine and the others look like cosine. And then the frequency is just the reciprocal. So it should be 1/2, right? And that's hertz, which tells us that that 1/2 of a cycle happens in 1 second. So if we go, this is like t equals 0, right here, well, like right here, and then here is t equals 1. So if it splits up, right, if this is the first half and then this is the second half, it looks like, I mean, that makes sense. So half of a cycle happened at this, right? Now, the reason it looks funny and it's not like perfectly even with our like curves, right, where it's like it stops right on the line or right up here or right in the middle. The reason it looks like that is because of this phase shift now. With, I guess could have a phase shift, but when we, for whatever reason, when we looked at this up here, we're not considering phase shifts. But maybe this problem is just to show you that, and I bet it's in your homework, that there can be a phase shift. And remember, a phase shift is B over, wait, is it C over B? It was C over B. So it's going to be, if we call this like C, it's going to be C over omega, which is pi over 4 over pi, which is the same thing as pi over 4 pi. And these can cancel, and we're left with 1/4. So far what we saw was that in 1 second, half a cycle, then we saw in 2 seconds, 1 cycle happens. And our phase shift just means that, notice how typically, so, I guess another way to figure out the phase shift, which I think C over B is way easier. However, this is throwing it back to when we first learned this. You can take, and let me erase things up here, but I should keep. You can take this entire pi t minus pi over 4, and you can write it as 0 is less than or equal to pi t minus pi over 4, which is less than or equal to 2 pi, right? The sine and cosine are always from 0 to 2 pi. So you can write it this way, and then you can solve for t. So this is also how you can get the phase shift if you're not showing long. So we add pi over 4 to every side, and then we get pi over 4 is less than or equal to pi t is less than or equal to, I'm just going to say 2 pi plus pi over 4, because we now divide by pi. So divide this by pi, divide this by pi, which, I mean, granted, this ends up on this side, we end up getting the phase shift, but divide by pi and divide this by pi. But we also get it here. So what this shows you, the final answer, what we get here, which I'll write it up there, is 1/4 is less than or equal to t, which is less than or equal to 2.
hold on, let me move this. Which is less than or equal to 2 plus 1/4. So you could either look to get the phase shift, you could either, look at this number or the number being added. They actually, I want to say they should be the same always, but maybe that's not true, but I think they should always be the same. And so this is the phase shift. Or you could remember that it's C, if you think of that as C over omega. Now, we just talked about these two equations that you see here next. And we have the sine equation that starts at equilibrium. We just saw that above. We have the cosine equation that starts at a maximum displacement. So the only difference here between the sine and cosine displacement equations is where they start. So even though it's always going to start at t equals 0, so maybe that's what's kind of throwing me off. It always starts at t equals 0 because we're starting with a time of 0 seconds, right? But depending on if you have sine or cosine, it's not about like how the graph looks so much as whether it's starting at an equilibrium point or at a maximum displacement. So maybe whether they're like starting with the block at a middle point or 0, or that's what I'm considering equilibrium, or if they're starting it at the very top and then dropping it and letting it, hang. So number 6, so this just says solve the formulas for omega. So this is just to figure out, we know how to get period and frequency. What is omega in terms of our period and our frequency? So let's check this out. So in the first case, we would multiply both, we'd multiply both sides by omega. So we get P omega equals 2 pi. Then we would divide both sides by P, right? So they'd cancel here, just like these cancel there. We'd get omega equals 2 pi over the period. So this is the relationship, which makes sense, hopefully, from the other equation. And then frequency is going to be a little different because, so notice how to get omega from the period, we're dividing by the period. But to get omega from the frequency, we're going to multiply both sides by 2 pi. And then we just get that omega equals 2 pi times the frequency. So we can think of it either way, but this makes sense because the frequency is just the reciprocal of the period, right? So this should be the case. This makes sense. And I think now we're going to look at a problem where maybe we're given some more information, or maybe we're given the period and frequency, but we need to find, well, I think we still have to find period and frequency, but then eventually we'll be given a problem where we have to find omega, possibly, right? And we would use these formulas. Now, I will say on a test or a quiz, on a quiz, you always have whatever formulas you need because they're open note, but on a test, I think I'll just put these formulas on there. If I don't, and you need it, please someone just remind me, because I don't mind. I think you should have access. No need to have to memorize these. I want you to know how to apply them, right? I know before we've had to memorize period and this type of thing, but Kevin, this is Home Depot. Can you just say like hi? Yeah. Hi, sorry, that's our that's an important call. That probably because they're on their way. We're getting. Life is crazy. We're getting flooring delivered tonight because it was delivered yesterday and they forgot some of the materials and it's being installed tomorrow. So I was on the phone for like an hour before class and trying to figure that out, but they're coming tonight. So the dogs will be barking. You'll know when the floor is here. The dogs will bark.
You're saying the formulas for the displacement will be provided?
Yeah, so displacement and then okay, I won't give you the amplitude formula probably because amplitude is A. I'm not like out of these three, I'm not going to provide amplitude most likely. If you asked me,
like during if you typed in chat or something, maybe I'd just say, remember it's A, or I don't know. But period, frequency, and omega, I will give those because I don't know. Maybe I'm feeling nice, or maybe I looked at a test earlier and my subconscious knows we just give it out. So yeah. Oh, thank you, Paul. So yeah, those formulas will be provided. And again, if you're taking the next test, however many weeks from now, and you remember and you see like, I don't see these formulas, just send me a chat and I will post, thank you. I will post the formulas, for you guys. Okay. So number says a block hangs on a spring attached to the ceiling and is pulled down 8 inches below its equilibrium position. So this is where, so now I'm picturing it a little better, and maybe you can too. We have a spring, right? Okay. Who the heck knows? We have some spring. If the block is at equilibrium, what that means is it's just still, it's staying still, and the spring is extended, right? And then what's happening is, like in this case, it's on a spring attached to the ceiling. Oh, wow. All right. So this would be a ceiling. And then someone pull block down and then it bounces, right? So if you pull the block from equilibrium and it bounces, and then at T equals 1, 2, 3, it starts moving in this sine or cosine pattern. This is what's happening when it starts at equilibrium. If it doesn't start at equilibrium, then the spring I picture is like this. The block is here and it's coiled up, and the spring is not released. And then you're dropping it. You're not pulling it. You're just dropping, and it's following some type of pattern, right? I guess what they mean, this stuff up here. Oh boy. All right. Bear with me. What they mean by this stuff up here is the sine is usually when it starts at equilibrium and then it's like pulled and changed or whatever. And the cosine is when it starts at the maximum displacement. So it's squished, the coil is squished all the way up, and then they're dropping it and letting it fall. Something like this, right?
Well, in the first graph on the previous page,
Yep.
it looks like, if you can, go.
Doesn't it look like they're both?
It looks like they pulled it down to 0. Or not.
So maybe
0.
it was at max. I know. So maybe, okay. And so maybe I'm saying this wrong, that they pull it to equilibrium and then let it go. I'm not really sure, but it's something like this. Cause I was trying to picture, how can you get it to be at equilibrium? You know what I mean? Like before doing anything. Because I always was just thinking, I was thinking
pushing it up and then it
right. They could be pushing it up and letting it go, or pulling it down and letting it go. Right. So it's something like this. It's something like this where that is the difference. Basically, they're either pushing it up or pulling it down. Right.
Mm-hmm.
I just forgot that you could pull it down. I was only thinking you have to start with it up. So I was confusing myself. But so in this problem though, we have, it's pulled down 8 inches, but the equilibrium. Okay. And then after the release, the block makes one complete up and down cycle in 5 seconds and follows the simple or a simple harmonic function. Okay. So in this case, we think about a few things. What is the period of motion? Well, they tell us one up and down cycle in 5 seconds. So period is 5 seconds. What is the frequency? Well, it's the reciprocal of that. I mean, I don't have to, oops. Okay. It says sketchograph first. I'm going to answer these questions first because it's easy. 1/5 hertz. Okay. Now in this case, well, what is the amplitude? I mean, it's being pulled 8 inches below. So it's going -8 down on a graph. So we would have like -2, 4, or okay, maybe that's not enough. We'd have -4, -8. So it's like starting down here, but the amplitude is 8, right? Because it's the absolute value of that and it's inches. And then to go back to B for a second, we want to think, okay, if you're thinking, is this sine or cosine? Well, it's starting, I guess, technically, since they're pulling it to the 8 inches, it's starting at maximum displacement. They're not like hit or moving the spring or however else. So that would mean it's this, because it starts at max displacement, but it's being pulled down. That's why it's negative. So if it's being pushed up 8 inches, then we'd be starting at 8 up above in our graph, right? But we're going to start at 8 down below. And then we know that, okay, so if this is like t equals 1, 2, 3, 4, 5, we know that at t equals 5, I'm going to end up back here because I'm going to go through one full cycle. And then we know, I mean, okay, we don't really know what the graph will look like, but look something like, you know, something like this. Because we're not going to have, because we start below, it's not going to look like the norm, you know, this 0. It's going to be a little bit weird in how we write this, right? And this, okay, although it's asking to sketch a graph over one period, I know that on a test or anything, you will not need to do this. So yes, sure, this is good to know. And really all that's important here, if you ever needed to do this, was where does it start and where does it end? And labeling your axes. So it starts at -8, 0, or 0, -8, right? And then it ends at 5 seconds because they told us one cycle ends in 5 seconds and it's at 5 -8. So that's really all I cared about. If this in between is a little bit weird, you know, I'll accept it. I think they're here. I think. No, it just, oh, did they say they'd call back? Oh, gotcha. Okay. All right, scratch that. All right, we're good. So now E does say write a function. So on a test or a quiz, I will either tell you like if we're starting at max displacement or not, and you should know, okay, that's sine or cosine, or I'll tell you it's sine or it's cosine. Like I'll just have the equation there and you have to get omega. So what we need to get really is omega. So what is omega? And to do that, we have our handy dandy equations that we came up with above. You can pick, it doesn't matter which one you use, right? We know the frequency and the period, but I'll just use the period to say omega is 2 pi over 5. So this is omega, and I get this. I mean, I'm using this, or you could have also used this, you know, it doesn't matter. And so if I want to write a function to model displacement in inches, I have D, and over a function of time, D is going to equal, well, I start at -8. So remember, even though amplitude is 8, I'm pulling down, so I'm at -8. Then I decided it was cosine because I'm at maximum displacement. I know that my omega is 2 pi over 5, and then I have T, right? So this is what I'm looking at here. And I think in your book, I mean, they might write this as D of T. Well, if you just write D equals, this is fine. Not. Okay, so I think we have 2 or 3 more problems like this. So let's check them out and see what we've got going on here. So again, more applications of the right triangles. We're still in this same little bit here. So number 8 says, suppose an object is attached to a horizontal spring subject to given conditions. Okay, they are saying subject, even though theoretically we're pretending there's no conditions, right? At time t equals 0, the initial displacement is 0 inches. Okay, so this is telling us it's starting at equilibrium, right? So this tells us initial displacement start at equilibrium, and that's going to tell us it's going to be sine, right? Excuse me. So, and it says moving to the right. Oh, okay. So this block it's a horizontal spring. That's kind of, but that exists, right? So, and it's going to the, so the amplitude is 16 centimeters. Wow. Okay. So A equals 16 centimeters. And I think the fact that it's moving to the right means A would be positive. If they said it was moving left, A would be negative. So just keep that in mind. And that, I mean, notice the picture here. So it's going to move this way. So way over here, it's going to be a positive 16, right? Whereas if it was moving this way, you'd see negative numbers, right? So I think that's like your little hint there. And then it's saying the frequency is 4 hertz. Okay, so F equals 4 hertz, which means right off the bat, my period is 1/4 of a second. So I know that one period is going to happen in 1/4 of a second because 4 cycles are happening in 1 second. Okay, so this is fine. Now what I want to do, what does it say? Find a model for the displacement function. So we want D equals something. And I know that we're using, because equilibrium, we're using sine. And I know amplitude is 16. So all that's left in this equation, remember, the equation is A sine omega t. That's it. We're not getting complicated, right? We're shifting here, even though I guess in some of the ones where they ask you, there's a shift. We're not going to do shifts in the ones that you need to predict. Well, at least for now, right? I think we have a possible case later of like one, but it's not a phase shift. It's something else. So, okay. So in this case, all I need to do is find omega. What is omega? Well, I can use either the frequency or the period, but remember my handy dandy equations from the previous page. Omega is 2 pi divided by the period or 2 pi times the frequency. So it might be easier in this case to do 2 pi times the frequency, which is 4, because dividing by a fraction is annoying, right? And so this means it's going to be 8 pi is my period. I mean, it's my omega, right? So now I know that my D, because it's going right, it's positive. So I have 16 sine 8 pi times t. And there's my displacement. And again, I think your textbook is going to have it like this. So if in your homework, if it might just already have D of t equals, but if it doesn't, just like know that that's what this means, right? But you don't need to be writing D of t. D is just fine. Now, well, okay, even though I don't really want to do this, but in my notes, I kind of sketched it out earlier just to look. If we look at just a sketch of, you do not need to graph this by any means, but I want to see like, what does this look like? And so what I'm seeing, if I'm starting at t equals 0, this is right 0. And then I know, okay. Well, I'll just do this. If this is like 1/8 of a second, 1/4 of a second. Okay. If this is 1/8 of a second, 1/4 of a second. And I'm splitting this up because 1/4 is 1 cycle, right? So I know starts at equilibrium. So that means at 1/4 of a second, I also know that this is 1 cycle, right? The period is 1/4. So at t equals 1/4, an entire cycle has gone through. And what that means is it's going to look something, and we know it goes up to 16 and down to -16. So it's going to look something like, okay, that was not perfectly even, but something like this, right? And it's sine. Now, keep in mind, sine, when you have sine, typically for one period, it should look like this nice curve up like a hill and then curve down and then ends at the same point. Whereas before, my graph for cosine, this was more like one hill. Like, so if we look at the previous question, it was more like one little hill, and sometimes it'll go down, sometimes it'll go up, but here we started at -8. If we had started at +8, like up here, it would have just went like this, right? So it just would have done. So keep in mind that cosine graphs, just if you're looking at the graph, I mean, typically this is what one cycle should look like. But again, if you started your cycle at a weird point, you could always, because this, because this technically continues, right? You could always like start it here, end it here, and it looks like sine. So sometimes they do that in the graphs and that's confusing, but if you were ever graphing it yourself or looking at something like this is another way to tell like, oh, one period from 0 to here, this was cosine, whereas this one represented like our typical sine curve. Okay, let's take a look at number 9. All right, now we've got a Ferris wheel. We're moving on from the gross cockroaches and snakes and whatever else we had to something pleasant like a Ferris wheel problem. Okay, so we have a Ferris wheel is 120 feet in diameter. So that means keep in mind like diameter is this whole thing, right? This is 120. And its lowest point is 2 feet off the ground. So this, its lowest point, which maybe that's there, this is 2 feet. 120 feet. Okay. The wheel makes one full rotation. Okay, so one full rotation. Counterclockwise in 2 minutes. Keep in mind, we normally do seconds, right? So I mean, granted, I do think we're gonna wanna, I think we can do this in minutes, but just keep in mind, you're 1 second now, one cycle, you're in cycles per minute, not per second. I mean, it doesn't really do much, like your number might just look the same to you, but just keep in mind, we are switching from minutes, from seconds to minutes now. And you could convert it back, but then your numbers actually be really big. So I'm immediately regretting that decision. We're just going to keep it in minutes. And I'm realizing here they tell us, figure it out in minutes for us. So suppose someone is seated at the lowest point. So you're wherever these chairs are, we're seated right here, right? And is the last passenger to be loaded when the wheel starts. So there's a million other people all sitting all around here. However, you know, here's all my stick people for us, like right, and they're all around. And the last person is loaded. Okay. Part A says write a model representing the last passenger's horizontal position, which is in feet, relative to the center of the Ferris wheel. So here, center's here. Their horizontal position, so they're here. So we know that this is actually 60 feet, right? Because then to the top, like the radius is 60 feet because the diameter is 120, right? So we know this, and we can think of it like points on the end here. And we can also think of this, what I've drawn from the green, like we can think of this green as like the y-axis, and the blue line, you can kind of think of it as the x-axis, right? And now we're picturing a Ferris wheel on a graph. Except maybe I'm actually drawing this wrong, and what we want to think about, because we're not sitting in the middle, we're sitting at the bottom here. And the Ferris wheel starts at the bottom. So this is actually going to be the x-axis. And this is going to be the y-axis. And keep in mind, so this will be 0, whereas this point will be 2. And then this point way up here will be actually 122, right? Because it's 120 diameter plus the 2 feet on the bottom. So we know, well, what do we know? We know that one full rotation counterclockwise. Oh, maybe I was moving the wrong way. So it actually moves this way, not right. Is that counterclockwise? Yeah, I think so. But doesn't so much matter. So it is moving this way though. It happens in 2 minutes. So that means that my period is 2. Right? Which means my omega, well, I can get my frequency. Frequency is 1/2 of a minute, which, is 30 seconds, but okay. And then my omega is 2 pi over 2, which is just pi. So this is pretty nice so far. Now, what we need to figure out is what is my amplitude? Because I want to write this equation, and it says the horizontal position X. So this is a little bit weird, but instead of writing so we're looking for the horizontal position. So it's going to be X equals something instead of Y equals, but we're still using we're still using A sine omega T. Okay. And, okay. And the reason we're using sine here is because we're pretending that we're starting at equilibrium at 0. So if we look at a graph here, technically, I guess this would be X, this would be T. And we are moving, so we've moved, I guess, nothing from the start, but we're looking at our position relative to the center. So relative to the center, if we start looking center, this goes -6. So if you do think of this, like I was originally saying, if you think of this as the x-axis and this is 0, then if we're sitting right here, we're sitting at -60, and the top of the Ferris wheel is +60, right? And so our horizontal position is, and it still takes 2 seconds to go full way around. So our horizontal position is something like this. Okay. Where we're getting to 2 seconds in one full rotation. Our omega is pi, and our maximum, so our amplitude here is going to be 60, not 120, because we're starting from, relative to the center of the Ferris wheel. So from the center of the Ferris wheel, you can never travel 120 feet. And we're not even considering the 2 feet below us, because we're thinking ourselves physically, we're sitting at the bottom of the Ferris wheel. It's 60 feet above to the center, and then another 60 to the top. So relative to the center, we're actually always going to be like about 60 feet away, below, above it, right? And then as we're moving along that circle. So that's this path that we're moving in here. But when we at the start and at the finish, we're exactly in between at 0. We're calling it 0, but we're exactly in between we're 60 feet away from the center. When you have to shift the graph up to, so Colby, in this case, because we're looking at the horizontal position, no, but in the next one, when we write the last passenger's height in Y, this above ground level, this we will add the 2 feet, but this we're looking at relative to the center of the Ferris wheel. So we're only considering our position relative to here. So even when I move and I go up and we're at the top, relative to here, we're still only 60 feet away. So we only we're 62 feet away from the ground, yes, but we're looking relative to the center. Okay, so a bit weird, but yeah, that's what this problem is asking. And so when we write this formula, which maybe now I can write it.
Can I ask you about one other thing about maybe it's the relative to the center thing.
Yeah.
It's, okay, so it takes 2 minutes to go all the way around. So 1 minute you're at the very top, right?
Yeah. So 1 minute you're actually still the same, but at 1 minute we're technically, we're 0. So this graph I drew, this means we're 0 distance from the center. This means we're relative to the center, we're okay, we're 60 feet away, but how can I explain this? Because we're considering this 0, because up here, so at half a second, we're over
Mhm.
here, and we're considering that, we're looking at the horizontal position. So horizontally, we're
Mhm.
60 degrees, we're 60 feet away, but horizontally here, we're
Yes.
in line, and so we're 0. We're considering that 0. We're not considering the height. We're only considering horizontal distance. So that's why we're only looking at these 60 and this 60, right? So when we first go
I
around
see.
this way, yeah, here we're at positive 60. Then we go back and we're back at 0. Then
Yes.
we go, okay, well, I'm going the wrong direction, but okay, you get it. Then
Yeah.
we go here and we're at negative 60, and granted, it's just reverse direction that I'm drawing, but then we're at negative 60, and then we're back at 0 where we started, right? Does that kind of
Right.
make sense? So we're only
Yeah,
looking at
that does. It's kind of counterintuitive, but it does make
It is
sense.
a bit counterintuitive, which is why I was not maybe saying it correctly at the beginning. So now what we see, we have this amplitude of 60, because 60 is how far the maximum horizontal distance we can go. So, and maybe what I should have done for Colby, and I know maybe you get it now, but this distance, like this distance is, 60 and 60. Right. But maybe that's negative 60, and but technically all of my previous arrows like were the wrong way. And so, which is why, if we go in this direction right here, I'm at positive 60 horizontally. Then I go up here and I'm back here, and that's back at 0. And then I continue down. When I'm here, I'm at negative 60, right? And then I go back to the beginning. So that's now I've drawn it actually correctly in the right direction. But Colby, maybe that helps with your question as well. And so now I know my amplitude is 6, not including that 2 feet, because that's going to be included when we're looking vertically. And so my equation is just x is going to equal 60 sine of pi t. And so based on wherever we are at all these points, right, you could calculate that, whatever the time is, and you could figure out what is the distance. It would be 60 times pi times the time.
For your horizontal distance.
Yeah, the horizontal. So that's like that's going to equal, this is like really weird to think about. That's going to equal the distance that you're at. So it's not time. It's actually going to be in feet, right? Or what? No, centimeters. What are we in? No, we're in feet.
It's in feet.
So it's going to, so if I person drew here, right? Let's follow this guy. Let me do a different color so that this might be too late. But if we follow this here, right? This person, they've traveled all the way around. Okay, let's just pretend. So they're right here. Their distance, or their horizontal distance that they've gone, is actually this whole light blue path that I've drawn. And so that would be, granted, their distance from this center is going to be, I don't know, maybe negative, 50 or something, almost to negative 60. But that's going to be their horizontal distance from the center here. So it's like the distance right here. And maybe it would have been easy to drew a person here because they're just starting to move. So as they start to move up this Ferris wheel, then from the center, you're slowly moving away. So they're moving, 10 feet, 20 feet, 30 feet, 50 feet. Then when they get to this exact point here, they're 60 feet away. Then they start to move back closer to the center, and then they move further away in the negative direction. Well, we're considering it negative, but just because we're pretending this is axes. So this is a very, kind of counterintuitive concept. Now, the intuitive way should be part B. So if we might write a model representing the last passenger's height, y, in feet above the ground. So this is above the ground level. Now we're looking at height. So now we're looking at everything height up this way. And so, well, maybe I should draw it again because now I've ruined my whole, my whole graph. So if this is time and this is y and y is the height, right? This is where Colby is right. We have to start at 2, right? We can't, like the Ferris wheel ground starts at 0, but we're starting, when we get into that and we start, we're 2 feet above the ground. So it's 2 feet above the ground. And then we also know it still takes 2 seconds to get to one full rotation, right?
Two
And we're going to
minutes.
end. Oh, sorry. Say that again.
2 minutes.
Oh, sorry. Second. Oh my God. I said seconds. Could you imagine? if
That would
we
be
had-
a very fast Ferris
Yeah,
wheel.
yeah. That's like a death Ferris wheel. All right. 2 minutes. 2 minutes. Thank you for that. So 2 minutes. And so this time, and technically it goes all the way up, like I was drawing before, to 122, right? But in the middle, it's at 62. We're just adding 2 to everything we know. And this is the equilibrium point in the middle this time. And so we're starting away from equilibrium because we're down. So now our graph is going to look thing, like this, right? And so this one's going to be cosine. And it's technically reflected, it's negative, just like it's actually similar to the previous example, 2 examples ago, right? Because normally cosine actually dips down when it's positive. So this is going to be negative. So amplitude is negative 60. It's still 60, but we're starting at 2, right? And because of that, I'll show you what we have to do for that like shift. So notice here, equilibrium is at 62. 62 equals y. This equals y. And so there is a vertical shift of this graph by 62. So what that means by positive 62. So, and it's not technically by 2, even though everything is shifted up 2, it would have been by 60, even if it was at 0. So what's happening is we still have omega is 2 pi over 2 because it's still 2 minutes, right? One cycle has not changed. So it's still pi. So my final function for y, my height y in feet above the ground level, is going to be negative 60 cosine pi t. But then this vertical shift adds a plus 62 at the very end. And again, these types of problems might be in your homework, but they should not be like in an exam. It's not going to be this kind of complicated. The exam is going to ask you, what's the amplitude? What's the period? What's the frequency? Or maybe it'll give you the frequency and period and say, what's omega? What's the equation? But we're not going to get, if there's a Ferris wheel question on there, we'll update this, right? So this is how we interpret that. And in our final equation for y, for our height, so our vertical equation is going to be this. And our horizontal is here. So next time you're on a Ferris wheel, you can think about this.
Calculate exactly your XY coordinates.
Yeah,
or
calculate your
whatever.
X and Y where you are. You'll just have to ask them, how high is this?
And how long
From the
is
ground?
it?
And then how high from the ground? I got to subtract that. Yeah. No, I'm just kidding. Okay, so our last type of harmonic motion problem that we're looking at, again with displacement, and we'll always, so these equations, I actually don't remember if, I'll have to double check for your test, but you would also be given this equation if you needed them, because these are these involve some exponential, right? Because this is the displacement of something oscillating under what they're calling here. Instead of that simple harmonic motion, which is what Michael was saying is more theoretical, right? This damped harmonic motion at this time t. And so, and what's going on here is there's a factor, what they're calling the damping factor, right? And that's some constant c greater than 0. Now, typically it's going to be given to you, or they'll give you everything else and say, solve for C, but I don't think we're going to do that here, but you could, but this number will be given to you because this is a number that like we're not responsible to calculate, right? Or typically. So the example here is going to be, well, you can see that T, we still have, if looking at these equations, we still have our A cosine omega t, A sine omega t, but then we have this e to the negative ct. That is what I would call like our maybe damping coefficient or damping like factor that is also related to the time, right? It's e to the negative c, and that's, you know, c is that constant, but the time is still in there, right? Because we need to factor in time. It's going to be, the damping factor should be different, or that coefficient should be different for every time. It's not going to be like, oh, at 1 second, that's the same. Whereas at 10 seconds, it's also the same. Like that doesn't make sense. So the example they give us here, displacement in inches. So now we're in inches of an object is oscillating under damped harmonic motion at time t in seconds. We're back to seconds from minutes. So now I can, you know, not keep mixing that up, is given by this. D is 10 e to the negative 1.4 t. So this tells us that c equals 1.4, right? Cosine 3 pi times t. So this also tells us a equals 10. So notice on the graph that they give here, you know, it's 0 and negative 10 to 10 is our range. So that makes sense. Then I notice the 3 pi times t, and this is our 3 pi is our omega. And then I'm at cosine, so that means I don't start at equilibrium, I start at a maximum. And in this case, we started, well, notice how the 10 is positive. So I started at positive 10, not negative 10, right? If it was negative, the amplitude would still be 10, but my graph would just be reversed. It would be flipped, right? Everything would start different. Now, for this one, notice how it follows cosine, but it also follows an exponential. And remember, when we looked at e to this whole thing, like e to the kt, or however, you know, e to the rt, when we looked at compound interest, when we looked at this, the graphs of that they would approach, I mean, they were a little bit crazy, right? They would be some type of lines like this, or just something like this with, you know, an asymptote here and an asymptote here. They were just a bit crazy. So if we combine this sine cosine with e, then we get something like this, where you see this curve. It starts out looking like it's going to be cosine or sine, but then it gets smaller and smaller and shrivels, and it's just going to keep going, right? And what's happening here is this function, the dotted function, is our exponential closing in on this function. So let me point this out. This is like y equals 10 e to the negative 1.4 t, and this one is y equals negative 10 e to the negative 1.4 t. And they call this an envelope function, maybe because it closes in on like an envelope. I don't know. And then you'll notice that, you know, we can see here at, I mean, this is about, I think this point is where cosine of 3 pi t equals 1. And this point, I mean, so approximately, well, okay, it's maybe not exactly that point, but approximately something there and approximately here. So maybe this isn't drawn to scale, would be where cosine 3 pi t equals -1. Because at some point it hits 1 and -1, and so do these, because well, okay, because they hit 10 over 10 or -10 over 10. And so what we need to calculate here, or what is it asking? Determine the time in seconds between two consecutive relative maxima. And so that's what we're going to look at here. We're going to think of this like, so think of this like the period, right? So period is going to be, well, omega, hold on, I'm forgetting what omega is 2 pi over period. So what did we say? Period was 2 pi over omega, right? Yeah. So period is 2 pi over omega. And so that's going to be 2 pi over 3 pi, which is 2/3. And so if this is 2/3, that's technically where this should be. And that's why I drew that before. So the time between two consecutive relative maxima should be 2/3. Are we in minutes again or seconds? 2/3 of a second. I think we're in seconds. Yeah. So think time between as the period, right? And then what is B asking? By what percentage? So, well, notice, I guess, just note before we answer part B, that we have amplitude was 10, the damping factor C was 1.4, and omega. Make sure, even though that's not asked here, those are things that you just should know, right? And at time t equals 0, like when t equals 0, D is 10 times e to the -1.4 times 0, which this just becomes 1. And then times cosine of 3 pi times 0. So cosine of 0, which this is also just 1, right? That's why it's 10. This equals 10 at the start. And part B is asking by what percentage is the displacement of the object decreased with each successive oscillation between consecutive maximum. So what this is asking is, in this whole, I mean, we have at t equals 0, D equals 10, right? After one oscillation, every oscillation is different now. They're not all equal because we're not on a simple harmonic function, right? But after one oscillation, I can't spell. Okay, however that is spelled. T is 2/3 because that's what we found in part A. And so D is, let's plug in 2/3, 10 negative e to the -1.4 times 2/3 times cosine of 3 pi times thirds, which is really just, so this is really just cosine of 2 pi, which we know, or wait, is that right? 3 pi
0.
times 2. Did I do that wrong? Because that should be 0, but that's not right. Did I write something wrong in this equation? 3 pi t. Yeah. Seems like this should be 0. So maybe I drawn this wrong, or maybe I I don't think that's supposed to be true though. Cosine of 2 pi. Oh, maybe maybe this is supposed to be in degrees. Degrees or radians before? We were always in radians, right? or up here, were we ever calculating? I think I might be messing up. This might need to be in degrees. Cause what calculate, just see if that's true, because if that is true, let me calculate. So what do we have? Cosine of 2 pi. No. Yeah, I'm not sure why I'm getting, because this should be 0, right? But it shouldn't actually equal 0. So I've done something wrong here, but I'm not quite sure what. But maybe, I mean, we're getting that this, so we're getting D equals 0. For some reason, we shouldn't get this, but yeah, I'm not entirely sure why. Because what that says is that like 2/3 then should be, well, should be maybe here, but that's 1/2. So unless this graph, it could be that this graph is labeled wrong. It might be that this here, it might be that this should be 2/3 and should be like closer to 1 or something like that. I'm not understanding if I did something wrong.
I see what you mean. Makes sense.
Yeah, it might be, so, because I'm just confused because this graph doesn't look right then, but perhaps it should, perhaps this should be 2/3 and it's just labeled 1/2. Because also if you look at this, if this is 1, I mean, I guess that could be 1/2, but that looks a little too far. Like 1/2 looks like it would be.
It says, I mean, is a period the amount of time between the maximus? Or is it something different? Each successive oscillation between, I don't know.
Okay, you can hear me, right? Even though, I'm not sharing anymore.
Yes.
Okay, well, so you won't be able to see me, and I won't be able to see chat, but, because my laptop, I mean, maybe it will come back, but maybe it won't. No, yeah, I understand, but my laptop doesn't, okay, so what I was saying was if we got D equals 0, which tells us that the displacement or the percentage, by what percentage is the displacement of the object decrease? Well, this tells if it's 0, it decreases by 10, right? Because it goes from 10 at time is 0 to 0 at time is 2/3, right? So it would decrease by 10. And then you could, that's like 100, that's actually 100%, right? But if D was 3 or something, right? So suppose, let's suppose this, and I'll write it in a different color. So this is what we actually got. But just so you guys can see, if D was about 3, then this means D goes from 10 down to, from 10 down to 3, so decrease by 7. And that means like a 70% decrease. Right? Because 70% of 10 is 7, if that makes sense.
So that's what's going on there. Now I'll save, so I know these notes are all connected. And again, if I figure out what's going on here, I'll let you guys know. But I guess it might just be that this graph was a little bit off and that, you know, this is the correct answer and it's 100%, but that just seems wrong for some reason. But if you have questions or come across a homework problem, just let me know. And I can, you know, figure that out. My computer might be joining, and if that's the case, we'll see. Oh, it is. Of course it is. Right at the end of class. So we'll. Okay. Well, I'll keep talking here, but you should be able to, I guess, hopefully see me now, and I'm just not joining audio. So here's what we have, and I just wanted you to see if it's not 100%, like what is it? And you could calculate this by doing like 10 minus 3 divided by 100, right? Or divided by 10. Oops, divided by 10. Because that should be 7, that should be 0.7, right? And this is 70%. That's how I did that. And how I did it up here was 10 minus 0. Like I took this 10 minus 0 divided by 10, and that's 1.0, which is how I got 100%. Yeah, something about that seems like I did something wrong, but maybe, who knows? Maybe that's not true. Oh, and maybe I meant one oscillation. No, yeah, that was the previous problem. Never mind. Don't worry about it. But so this is what we're getting here. And well, this is the end of the notes for today as well. Oh, question of the day, so that I can put that up there. Let me see what I had decided. Today will be, oh, we're close to Halloween, so I was thinking of Halloween things, but I know we've already talked about costumes. So today is just going to be, do you prefer like a comedy movie or a scary movie? It'll be something easy. I'll do a Halloween theme more on Thursday. But some people like a funny movie, or, I mean, yeah, you can totally like both. David, same. But sometimes, and it depends on my mood sometimes, right? But yeah, comedy or scary. So there's the question for today. And I will save these notes and get these up, you know, tonight. And just keep in mind that the notes for, let's see, the notes for Thursday's class are the same exact notes that I just pulled up, but they're going to be starting, you know, here, starting at 7.2 and 7.3, right? So they'll start there. And I don't need to save those, but let's hope I did save these. Yes. Okay, good. So I will post this tonight online. And if there's any questions, a dark comedy, I love that, Michelle. Yeah, that could happen. But yeah. And we only lost service at the end of the night. How great is that?
Time to do your floors, I guess, or whatever.
Yeah, now, well, apparently the floors are going to get delivered, I don't know, tonight. So now we can't go to bed.
At least it's not raining, you know.
Well, okay, very true. And they're being installed tomorrow. So hopefully, well, I guess they'll be inside by then, but well, there's a tornado watch yesterday. I didn't realize it until it was like already happening. And that was pretty serious. I